Hello and welcome to 9.4, the comparison of series test. Okay, to this point we've compared similar series. Now we'll compare a series one that's more complicated with a simpler series. That's the comparison test. So the direct comparison test, the first one we'll look at, there are a couple of comparison tests. Direct comparison test. So the series A sub n is less than B sub n for all n, but they're both positive. If the sum n goes from 1 to infinity, B sub n converges, then A sub n must converge. Because if B sub n, which is bigger than it, converges, sum goes to a fixed value, A sub n also converges. But if A sub n, which is smaller, diverges, B sub n must definitely diverge, must blow up. So use direct comparison to determine the convergence or divergence of the series. So I'm going to compare this to something simpler. Right now it's 1 over n squared plus 1. Well, 1 over n squared plus 1 is less than 1 over n squared. Right? And the sum, 1 over n squared, converges by, I think it was theorem 9.11. We'll call it the p-series test. Remember that if the power is more than 1, it will converge. Therefore, by the direct comparison test, the sum as n goes from 1 to infinity of 1 over n squared plus 1 converges. A lot of writing there. I feel like it's an English class now. What's that all about? Okay, so that was a direct comparison. Let's go on to the next one. Here we have the sum n goes from 1 to infinity of 1 over 4 times the cube root of n minus 1. Now 1 over 4 times the cube root of n minus 1 is less than 1 over 4 times, actually it's greater than 1 over the 4 times the cube root of n. And we could look at, okay, what about the sum of 1 over 4 times the cube root of n? Now that looks really complicated. We can write that as 1/4 times the sum n goes from 1 to infinity, 1 over the cube root of n. We could also write that as 1/4 times the sum n goes from 1 to infinity of 1 over n to the 1/3. So by the p-series test, theorem 9.11 I think it is, the sum n goes from 1 to infinity of 1 over n to the 1/3 diverges. So that one's going to diverge. Now, it's smaller than the other one. This one diverges, therefore the original must diverge by the direct comparison test. Because something smaller diverged, the bigger thing must diverge as well. So that's the direct comparison test. We're going to go on now to the next page and look at the limit comparison test. Okay, so the limit comparison test is that suppose that A sub n is positive and B sub n is positive, all those terms, and then the limit of as n goes to infinity of A sub n over B sub n equals some fixed value L, where L is finite. Then the two series either both converge or diverge. The nice one about this, you don't have to make sure you pick one that's smaller or bigger or whatever the case may be like the direct comparison. You could pick one that's similar where you would know its limit. You could tell what its limit's going to be. So it wouldn't have to be, it's not as critical which one's bigger and which one's smaller, trying to figure that out. So use the limit comparison test to determine the convergence or divergence of the series. So I'm going to compare this with the sum as n goes from 1 to infinity of 1 over n. Why 1 over n? Because if you didn't have that 1, n over n squared is 1 over n. Now we know what this one is. This is the harmonic series, and we know this one diverges. This is the third time we've talked about this one. So we have the limit as n goes to infinity of n over n squared plus 1 over n. It really doesn't matter which one you put on top, but here we go. That's going to be the limit as n goes to infinity of n over n squared plus 1 times the reciprocal of this, n over 1. That's n squared over n squared plus 1. And as n goes to infinity, that's going to be 1. So since the sum as n goes from 1 to infinity of 1 over n diverges by the limit comparison test, the sum as n goes from 1 to infinity of n over n squared plus 1 diverges. Okay, so we have a divergent series. So we compared the limits on that. Limit became a fixed value. Doesn't have to be 1, it just has to be a fixed value. And since one converged or diverged, the other diverged. We're going to move on to 4 here. Use the limit comparison test to determine the convergence or divergence of the series. This is n over n plus 1 times 2 to the n minus 1. Interesting that we have this 2 here in this one. So what if we compare this to one over 2 to the n minus 1? Now we'll just caution you, this is the same thing as saying n goes from 0 to infinity, 1 over 2 to the n. Because that minus 1, if you put 1 in there, you get 2 to the 0 for the first one. This is now a geometric series, and this is a convergent geometric series. Because r equals 1/2, the opposite value of 1/2 is less than 1. So we do the limit as n goes to infinity of n over n plus 1 times 2 to the n minus 1 over 1 over 2 to the n minus 1. That's the limit as n goes to infinity of n over n plus 1, forgot my parentheses, 2 to the n minus 1 times 2 to the n minus 1 over 1. So limit as n goes to infinity of n over n plus 1 is just going to be 1. Therefore, by the limit comparison test, the sum as n goes from 1 to infinity of n over n plus 1 times 2 to the n minus 1 converges. That's it. go to the next page. Last page for this section. Prove that if P of n and Q of n are polynomials of degree j and k respectively, then the series, as n goes from 1 to infinity, P of n over Q of n converges if j is less than k minus 1 and diverges if j is greater than k minus 1. Okay, so j is the degree of the numerator and k is the degree of the denominator. So let's look at the two cases. If j is less than k minus 1, then k minus j would be greater than 1. That means the power down below is more than 1 bigger than the power above. The P series with P equals k minus j converges since the limit as n goes to infinity, excuse me, my voice is giving out, of P of n over Q of n over 1 over n to the k minus j is equal to L, which is greater than 0. This series converges by the limit comparison test. However, if j is greater than or equal to k minus 1, then k minus j is less than or equal to 1. That means the difference between the powers on top and bottom is less than or equal to 1, which implies the sum as n goes from 1 to infinity, P of n over Q of n diverges by the P series test. Or diverges by limit comparison tests. Because the limit as n goes to infinity of P of n over Q of n over 1 over n to the k minus j would equal L, and because k minus j is less than 1, the sum 1 over n to the k minus j is divergent. There, by P series tests. That's it. So that was all writing. Again, is this an English class? So we're going to use the result from example 5 to do example 6. I'm going to scroll. Use the polynomial test from example 5 to determine whether the series converges or diverges. So let's think about what this series is going to look like. We have 1, 2, 3, 4, 5. There's just an n on top. 2, 5, 10, 17, 26. Okay, what I'm seeing here, this looks like it's a 1 squared plus 1, 2 squared plus 1, 3 squared plus 1, 4 squared plus 1, 5 squared plus 1. So it looks like it's going to be an n squared plus 1 down below. So in this case, our j equals 1 and our k equals 2. So k minus j is 2 minus 1, which is 1. So this is the second case. So the series is divergent. You can kind of see it too. If you were just not to have that 1 n over n squared is 1 over n, harmonic series divergent. Okay. And that's it for 9.4. Okay, thank you. Let me know if you have any questions.